Hello and welcome to our lesson on relative extrema. So what is a relative extremum? That's the singular version for extrema, which is our plural. A relative extremum, or multiple relative extrema, try to get that in there, are just referring to maxes and mins. So they are maximums or they are minimums. And we are going to be referring to these maximums or minimums as relative, or sometimes we use the word local, if they are on open intervals, but we call them relative or local maxes or mins or extrema because they may not necessarily be the absolute highest or lowest points for your function, but if you're looking at some local or relative region, in that local or relative region, if it is a maximum, a highest point, or a minimum, a lowest point, then again it's going to be called a relative or local maximum or minimum. So again, these are referring to highest or lowest points that are in a relative or local region. So relatively speaking, in this particular area, is this a maximum or a minimum? Okay? So we got to be able to identify these, and if we're looking at a graph, it's super easy to do that. But we're going to be focusing on, after we get the concept here, the mathematical way to find these extrema. So if we were looking at this picture, hopefully you can see some maximums and some minimums. So for example, right here we have a maximum, right here we have a minimum, and right here we have a maximum. And those are relative. Again, in this region, the point here is, let me get another color. In this region, that green point I highlighted there would be a relative maximum. So it's relative to that area. And this would be a relative maximum, again, relative to that area. And this would be a relative minimum, relative to that area. Okay, so these are our maxes and mins. We can kind of think about them as peaks and valleys, or like tops of hills or peaks, and bottoms of the valleys there, bottoms of hills. But if you notice what's happening, I think in terms of calculus, right? Where are these extrema happening? So they're happening at places that we just discussed in our previous topic, so at critical numbers. If we look at this first one I highlighted here, here we have a slope of 0. That means our derivative would be 0. So if m is equal to 0, that means f prime of x is going to be equal to 0. Same thing's happening here. We would have a slope of 0. That means f prime of x would be equal to 0, and I'm just assuming this function's called f of x. And then up this other one up here, we don't have a defined slope at this spike in the graph, so here our slope would be undefined, but again that means our derivative would be undefined. And those are precisely what we defined as our critical numbers. So the critical numbers are where the slope is 0, or the slope or the derivative is 0 or undefined. Now, they also happen to be places where our graph is changing from increasing to decreasing. So if we look here, our graph is increasing till we get to that maximum, and then it turns, and it's decreasing till we get to that minimum, and then it turns, and it's increasing again till we get to this peak, and then it's changing direction again after that peak. It is decreasing. So if we can identify the critical points, right? We know how to identify the critical points. If we can then determine where our graph is increasing and decreasing, if we're not actually looking at the graph, we can still know that if we change from increasing to decreasing or vice versa, that critical point has to be a relative max or a relative min. And specifically, if we're going to go from increasing, I need another color here. If we're going to go from increasing to decreasing, we have to have a maximum, and if we're going to go from decreasing to increasing, then we have to have a minimum. Alright, so that's the concept. It's really going to be like an extra step from what we talked about in our previous lesson, but let's write some things down here. A relative extrema, or a relative extremum, is going to occur at a critical number. So these occur at critical numbers. And as we just mentioned, critical number is of f of x is going to be where f prime of x is either equal to 0 or where f prime of x is undefined. Okay, and if we can identify those critical numbers, at those critical numbers is where we're possibly going to have our extrema, but not necessarily, and I'll show you an example where we have a critical number that isn't an extrema, but if it is, then our graph is going to be changing from increasing to decreasing or vice versa. So if the function changes from increasing to decreasing, again, increasing to decreasing, that's when we have a maximum. And if our function is changing from decreasing to increasing, that's when we'll have a minimum. Alright, so how do we go about finding these? Again, if we have the graph of a function, it's really easy to just look at the graph and go, oh, I can see it. I can see my critical numbers. I can see my relative maxes and mins. That's not the issue. Although we can use that to verify our work, we need to be able to do the algebra. How do we algebraically find these things? So we're going to use what is called the first derivative test to find our relative extrema. It's the same process we talked about in our previous topic, just with an additional step. Okay? So we're going to find the critical numbers, because those are the places that we're going to have our relative extrema. And we know that after we find our critical numbers, we're going to go ahead and test values that are before, between, after, depending on how many we have, to see where our graph is increasing or decreasing. And then if we see a change, again, from increasing to decreasing, it indicates that that critical number is going to be a relative maximum. And if we see a change from decreasing to increasing, it means that that critical number is going to be a relative minimum. And if we don't see a change, and actually I think in our previous topic we had some examples where we had a critical number but we were decreasing before and after, so there's no change, which can definitely happen. We may have a discontinuity or an inflection point instead. So if there's no change, then it indicates our critical number is not an extremum. Alright, so if we can apply the same process we talked about in our previous topic, and then afterward just analyze the work, we can figure out if those critical numbers are relative maxes or mins. So let's try it out, and we're going to start with my favorite type of function to differentiate, which is a polynomial, applying our power rule here. So if I want to find my critical numbers, remember I want to find where my derivative is equal to 0 or undefined. So I got to start this process by finding the derivative. So I got a 6x squared here, minus 6x, and then minus 36. There it is. Done. Derivative so easy when it's a polynomial. Now I got to figure out where this is either equal to 0 or undefined. Now it's not going to be undefined anywhere. Polynomial is continuous over its entire domain, so I don't have to worry about that. But I do need to, again, try to figure out where with 6x squared minus 6x minus 36, where it's equal to 0, because I will have critical numbers at those places. So I need to solve this quadratic equation. I'm going to start by dividing out a factor of 6, so that I'm really just trying to solve x squared minus x minus 6 equal to 0. And you could use quadratic formula if you're comfortable solving that way, but this is factorable. There are factors of negative 6 that make negative 1. Those would be a negative 3 and a positive 2. So this would be the factored form for that quadratic. And then making just one of my factors equal 0 would make the whole equation equal 0. So one solution comes from this first factor. X is going to be equal to positive 3, because positive 3 minus 3 makes a 0, and again, anything times 0 makes that whole equation 0. And then here I can see my second solution at negative 2. So those two solutions to that quadratic equation are my critical numbers. These are the two values of x that make my derivative equal to 0. So again, can't be undefined because it's a polynomial, but I want to make a number line here with my critical numbers. So I'm going to put, let's just pretend that was a straight line. That's good enough. So I'm going to put negative 2 over here. I'm going to put 3 over here. I need to identify the behavior that's happening before, between, and after these critical numbers, because if I know if my graph goes from increasing to decreasing or vice versa, then those critical numbers are maxes or mins. So we need to test some numbers. Let's test something like, how about a negative 3 over here? Let me change colors again. Let's test like a negative 3 over here, I like 0 if I can use that, and then maybe positive 4. Now you can absolutely do this work by hand, or you can just go to the calculator, but remember the work that you're trying to do is you're trying to figure out the behavior of the derivative here, because the behavior of the derivative is telling us the behavior of the slope, and if the slope is positive, the graph of the function is increasing. So we're plugging into our derivative. So we're trying to find f prime of -3, we're trying to find f prime of 0, and we're trying to find f prime of 4. And we really don't need the value, I just need to know if it's positive or negative to tell me if my graph is increasing or decreasing. So if you wanted to just use your calculator, you could. You can just type your function in there and swap out the x values. Sometimes I like to use my table feature to do this as well, because I get a little lazy of rewriting numbers. So I have x's here, and then I have x's being squared, minus x, and then minus 6. So if I just put my function here, then I can go ahead and input -3, and then input 0, and then input 4, and it spits out the outputs for me. So I kind of like that feature. Now if you're going to do this in Desmos, notice that in that first column, it called xx1. So in column 2, when I type x in there, I have to do x1, x sub 1, excuse me, to make sure that it connects the actual x values in my table to my function values. So I like that as an option. However you want to do it by hand, you want to just plug them in individually, whatever floats your boat. So f of -3 ends up being here, come on pen, +6, f of 0 ends up being a -6, and then f of 4, again, a +6. So I am positive over here, negative here, and then positive here. So that tells me that this interval is increasing, this interval is decreasing, and this interval is increasing. So I am changing from increasing to decreasing here, and then I'm changing from decreasing back to increasing here. So these are both relative extrema, just need to decide which one is which. So again, increasing to decreasing, that means I have a maximum. So I have a relative maximum, we will say at x equals -2. And then in this one, I'm going from decreasing to increasing, which means I have a relative minimum at x equals 3. And there's the algebra that we need to find those relative extrema. Okay? Now again, we have calculators, and you have the option to use Desmos when you're taking your quiz, when you go to take your midterm, which is quickly approaching. You'll have this. You can use it, and please use it to verify your work. But you're not going to get full credit on anything if you do not actually show me the work. Okay? So be prepared to do the work, but definitely verify that it's right. So what we've found here is that we should have a maximum at -2 and a minimum at x equals 3 for f of x. So let's put our original function in here and make sure that that's the case. So 2x to the third minus 3x squared minus 36, oops, in the subscript. Don't mind my fat fingers. Alright, so here's our function. Let me zoom a little bit here. And I can see, yep, right there, I have a maximum at -2, and boom, right there, minimum at x equals 3. And those corresponding y values would be really easy to find using that graph as well. So if I said, at what coordinates do we have a relative maximum, or at what coordinate do I have a relative minimum, then you would want both pieces to that, but I'm really okay just giving the x value. If you did not have the calculator, then you would have to plug these x values into your original function to find those corresponding y values, but not work that's going to be necessary, but if you wanted to do it, you could. Alright, so got an easy one out of the way. Now, so for a little bit of variety and practice with some of our other derivative rules, I have some different types of functions. Same process though, okay? So I want to find any relative extrema for this function, which means I need to find the derivative so I can get the critical numbers. So this is a product of two functions. Hopefully you're remembering, right? Here's our first function, x. Here's our second function, e to the 3x. So I'm going to call this f, and I'm going to call this g. So f prime of x, using our product rule, would be f prime g plus f g prime. So we're going to say f prime of x is... the derivative of x is just going to be 1, and then g is e to the -3x, plus f is x, and then the derivative of e to the negative 3x, remember derivative for e is itself, so e to the negative 3x, but then we want to use our chain rule, apply our chain rule, because this is not just an x, so we multiply by the derivative of negative 3x, which makes a negative 3. So there's our unsimplified form. I'm going to go ahead and clean this up just a little. So we have e to the negative 3x here, and then negative 3x e to the negative 3x here. This would be a perfectly acceptable form of the derivative. Now, if you remember back to our previous module, sometimes we were factoring in these situations, sometimes we weren't. If you're just finding the derivative, you really don't have to, but you're going to see why factoring is super handy here. So let's say I didn't factor, let's say I just left my derivative in that form. Remember, what we're trying to do next is find where this derivative is equal to 0 or where this derivative is undefined. So let's start with where is it equal to 0? E to the negative 3x minus 3x e to the negative 3x. Where is this thing going to equal 0? Well, in order to solve this, factoring is going to be super helpful. Now, factoring isn't the only way, but to me, the most obvious way. I can show you another way too if you want. You're out there saying, no, please, just give me one. But this is factorable. If I can get it in factored form, then just like the polynomial, making each of the factors equal 0 will get me my solutions. So I'm going to factor out the e to the negative 3x. That's going to leave me a 1 and then a minus 3x. And so now one of my solutions comes from making e to the negative 3x equals 0, and one of my solutions comes from making 1 minus 3x equals 0. Now, I'm going to run out of space, so give me a second. I'm going to go to move this. Okay, so here, can I make e to the negative 3x equals 0, I guess would be a question. That's an exponential function. If you know anything about exponential functions, they basically, well, this one is going to be a decreasing function. It's going to look like this. It's not going to get to 0. No matter what I plug in here for the exponent, no matter how big or small the exponent is. So think of a number that you can grasp a little nicer, like 2. If you have 2 to the first power, obviously that's 2. 2 to the second is 4. 2 to the third is going to be 8, and that increases exponentially this way. If you make the exponent, let's say, smaller, let's say you go 2 to the 0, well, then you get a 1. And then if you go negative, like 2 to the negative first, well, then you get a half. And then 2 to the negative second would be a fourth. And the smaller you make this, the smaller the fraction gets, but it's going to get infinitely small and it can't get to 0. So it's going to be impossible to make e to the x equal 0. So that's not going to get me a critical number. This is not possible. There will be no solution there. Let's say that instead. And over here, this one's linear, we can easily solve. So we subtract over the 1 and divide the negative 3, so positive 1/3 is going to be a critical number for us. Alright, so now let's test. Oh, and that's where our derivative is equal to 0. Can we make this derivative undefined? Would be the next question. Okay, well, I don't know. This kind of goes with the other way you could solve. So when you have a negative exponent, remember, you could move that to the bottom of the fraction, so you could make that 1 over e to the positive 3x and negative 3x over e to the positive 3x if you wanted. Because you're trying to think about where this thing could be undefined. The only way this would be undefined is if the bottom of these fractions ended up being 0, and that can't happen. We just said e to the 3x can't get to 0. E to the negative 3x, e to the positive 3x is the same thing. They can't get to 0. So this is not going to be undefined anywhere. So x equals 1/3 will be our only critical number. So let's go ahead and put 1/3 on our number line and decide what we want to test. So how about we test 0? I like to use that when I can, and then a positive 1 would be nice. And let's go ahead and plug this in. So remember, we want to find f prime of 0 and f prime of 1. So this time, I'm going to take a different route. I only have 2 inputs, so I have e, and I have to raise that to the negative 3 times, oh, I said 3, I swear, times, what are we plugging in for x? Let's put a 0 in there first. And then to that, I want to subtract 3e raised to the, again, negative 3x, and I'm putting a 0 in there. And I forgot a factor of x here. Don't make that mistake. And 0. Okay, so 3 places to plug in, right? Be careful. We have 3 x's to replace with 0. So that gives me an output of 1. So f of 0 is equal to 1, and then I'm just going to replace those zeros with 1s. And so there's your other option for evaluating. So we get like a negative 0.099, whatever, it doesn't matter. I just need to know if these are positive or negative. So over here, I have a positive 1, which means this is going to be increasing. And then over here I have a negative, which means this is going to be decreasing. So our graph is changing from increasing to decreasing, which means we have a relative maximum. So we're going to say we have a relative max at x equals 1/3. And then again, this would be good to check with your graph, especially because this is a function that's probably not like pictured in your head. Some of these functions, like the first one, I'm kind of hoping that when you look at a cubic function, you have some sort of an idea of what that looks like graphically, but I don't know. If you're looking at x times e to the negative 3x, do you have any idea what that looks like? Like, I have a concept, but yeah. So let's go ahead and graph and verify. So we're going to put in here, again, x, and I missed an equal, x, and then an e, and then we're going to raise that to the negative 3x power, and I'm looking for, what did I say? A relative maximum at 1/3. And we're way zoomed. And if you, yep, there you go. So if you go to x equals 1/3, you can kind of see, there it is, 0.3, repeating 1/3, we have our relative maximum. Okay? So we got the algebra in there, but the graph nicely verifies that work. All right, let's look at another one, I guess, just so we can practice using some of our other differentiation rules. So here our function is a natural log function. Remember, the derivative of a natural log is 1 over x, or in this case 1 over that fraction. So my derivative is going to be 1 over, instead of x, 5x squared plus 4 over x squared plus 1. And then because that's not just an x, I have to multiply by the derivative of that thing, which means I have to use my quotient rule. So I'm going to call that f and g. I want f prime g minus fg prime over g squared. That's the derivative of the inner function that I have to multiply by. So I'm going to have another fraction here. Go back to blue. Another fraction here. The bottom's easy, so x squared plus 1 squared. Let's get that done. F prime is going to be power rule in there. It's going to be a 10x, and then g, x squared plus 1, minus f, 5x squared plus 4, multiplied by g prime, which would be a 2x. Okay, so there's the unsimplified form. Remember, we're going to be doing some solving with this, so it's definitely going to be in our interest to go ahead and clean this up. So let's start with this, fraction in a fraction. So think about something simpler, right? If I had 1 and if I was dividing it by a half. 1 divided by 1/2 is the same as 1 multiplied by 2 over 1, or just 2. So I don't want to divide by that fraction, I want to multiply by its reciprocal. Well, if I multiply by 1 by its reciprocal, I'm just going to end up with its reciprocal. So this is going to become an x squared plus 1 over 5x squared plus 4 times, over here, I'm going to leave this denominator alone, and work on the numerator. So that's going to be a 10x cubed, and then I'm going to have a plus 10x, and then I'm going to just move this minus over here, so that's going to be a negative 10x cubed, and then a negative 8x. Okay, so we can simplify, we can do some reducing here. Let's see, 10x cubed and negative 10x cubed, those are going to cancel. I also have an x squared plus 1 here, so I can get rid of one of these, and I'll still have 1 left. and let's go with that for now. So what am I looking at in my numerator? Well, I combined 10x and negative 8x to make negative 2x. And then in my denominator, I'm going to have the 5x squared plus 4 to multiply by that one factor of x squared plus 1 remaining. And I don't actually need to multiply that out, so that's going to be fine. So this is our derivative. Now we want to find where is this derivative equal to 0 or where is it undefined. So let's start with how can I make negative 2x over 5x squared plus 4 times x squared plus 1. How can I make that equal 0? Well, remember, the goal is going to be to make the numerator equal 0. If I make 0 a fraction, then I can easily cross multiply and it zeroes out that whole denominator. So 0 equal to negative 2x times 1. Again, make that numerator equal to 0. So 0. When x is 0, then our derivative is equal to 0, so 0 is going to be a critical number. And then if we can make this fraction or make the function undefined, we can get other critical numbers. So anytime we have fractions, there's that possibility. It would be undefined if I can make my denominator equal 0. So f prime of x would be undefined if our denominator, 5x squared plus 4 and x squared plus 1, was equal to 0. But that's not going to happen because I can't make either one of these equal 0. So think about 5x squared plus 4, for instance, trying to be equal to 0. If you subtracted the 4 divided by 5, you would be looking for the square of a number to be equal to negative 4/5, and that can't happen. And the same thing over here. X squared is not going to be able to equal a negative 1. You can't square a number and make it negative. So there's no solutions here, which means no places where the derivative is undefined. So we just have the one critical number. So let's put that on a number line. And I made all this space, and I don't know, yeah. Not enough colors. On our number line are one critical number of 0, and then I need to test some things before and after. So I'm going to go with a negative 1 and a positive 1. So f prime of negative 1, f prime of positive 1, and we'll figure out what's happening. So my function is a fraction with a negative 2 times, let's go with negative 1 first. And then the bottom, what a mess. 5 times a negative 1 squared plus 4 times a negative 1 squared plus 1. Okay, so we end up with, I'm going to go ahead and get the fraction. I like that better, that little fraction of decimal button there. So f of negative 1 ends up being a positive 1/9. And then if I plug in the negative 1, I just need to go out and delete these. And I get a negative 1/9. Okay, so now I know here I am increasing and here I am decreasing. And so again, increasing to decreasing tells me that at x equals 0, I have a relative max. So a relative max at x equals 0. Alright, so let's verify. Again, this is going to be a funky looking graph, this original function. I don't know if you would have any clue what that looks like. Even I'm a little curious. So let's get the natural log. Did I miss it? Oh, don't mind my dogs. And actually, not my dog. My dog never barks, but I am babysitting, dog sitting 2 other dogs, and they are busybodies. Okay, so natural log of the fraction 5x squared plus 4 squared plus 1. Okay, so here it is, and we said at x equals 0, and if you zoom in there, boom, we have it. X equals 0, we have a relative minimum. And that's not what we said. What did I do? Let me undo my work here because somehow I miscalculated something. Oh my goodness, you're probably telling me this whole time. That should be a positive 2, which means this should be negative and this should be positive. Goodness gracious. I can add, I swear. 10 minus 8 is definitely positive 2. I'm so sorry. Okay, I'm so sorry. But at least I caught it, and this is why we verify our work, right? I did this on purpose, just so you can see how important it is to verify. That should definitely be positive. Positive. It doesn't change our critical number, it just changes the signs of the outputs when we plug in -1 and 1, and so this is not right anymore. Okay, so at -1 we get the -1/9, and at +1 we get the +1/9. So this one is, I am so sorry, this one's decreasing, this one's increasing, so this is going to be a minimum. Goodness. Again, important to verify your work. Ay, ay, ay. Okay. So, yeah, we saw it. I'm not going back in there. Alright, we got one more, and hopefully I don't goof this one. Let's end on a strong note, right? Let's try to differentiate, find our critical numbers, and see what's happening here. I am going to start by rewriting this function. I don't want that fraction in there if I don't have to have it in there. So I'm going to change that 1 over x to x to the negative first power. Just move it to the top. And now I can use my power rule. So f prime of x is going to equal, the derivative of x is just 1, and here if I multiply, I'm going to get a +1 in front of my x to the -2. So again, I'm going to rewrite this as 1 plus 1 over x squared. So where's this thing going to equal 0? Where is it going to be undefined? Let's start with, can I make 1 plus 1 over x squared 1 over x squared, can I make this equal 0? Well, let's see. I subtract the 1 over and make it a fraction so I can cross multiply. I'm hoping you can already see how this is not going to work. If I want to cancel this +1, then I need to make this a -1, and I can't do that. I can't square a number and make it negative. But if you wanted to go through the motions here, -x squared equal to 1 means, again, x squared would be we would have to make x squared equal to a -1. That can't happen in the real numbers. It happens in the imaginaries, but not in the reals. So there's no real solution to this. I should have specified that earlier. No real solution. So no critical number there. The derivative cannot be equal to 0. But we can make the derivative undefined here. So 1 plus 1 over x squared is undefined at x equals 0, because if I put a 0 in there, I get a 0 on the bottom of that fraction. That's no good. So 0 happens to be our critical number, once again. So let's go 0, and then again I'm going to go with my old reliables, -1 and +1. Find f prime of -1, find f prime of +1, and see what happens. Luckily this is a nicer function, so I don't have to plug so much in. So 1, I don't even need a calculator for this. What am I doing? If I plug -1 in, -1 squared is 1. 1 over 1 would be 1, plus 1 would make 2. And when I plug a +1, I get the exact same thing. So this is going to be positive and increasing here, positive increasing here. So we go from increasing to increasing, which means we're not changing. So there's a couple different ways that this can happen. You either have like an inflection point, terrible, an inflection point where we're increasing all the way through, but we end up with a 0 slope. That's not what happened here because it's undefined. So what's happening here is we probably have a discontinuity. So we have like an asymptote, maybe something approaching this way and like this. So no, that's not right, because they both have to be increasing. Okay, so I'm not drawing this out very well, but anyway, we're not changing, so it has to be an inflection point. We have to be doing this type of deal where we're increasing all the way through, right? So we have a critical number because we do get a slope that eventually zeroes out there, but no change in terms of increasing to decreasing. So no change means no extrema. So no extremum, or plural, or singular. Either one would be okay for that answer. Alright, now let's just verify, because strike 2 would be really terrible. What does x minus 1 over x look like? What do we say at 0? Yeah, we have an oblique asymptote happening in this graph. But this graph's going to go up forever, down forever. There's no tops or bottoms of any peaks or valleys there. So yeah, no extremum. And now that I said that, I want to throw something back into the beginning of the notes. I don't know why I didn't do this earlier. So we want to think about these maximums as peaks, and the minimums as the valleys, the tops, the bottoms. I think you're probably good there, but yeah, I just had to, so my brain's all over the place right now. I'm going to blame it on having extra dogs in my house, so yeah. Hopefully you're good to go for your assignment. If not, you have any questions, you need some extra help, then by all means reach out. Until next time, take care.